Hello everyone. In this video I will solve homework 4. So let's start for the first question. A unity feedback control system with the following open loop transfer function. G of s multiply with h of s equal k over s multiply with s plus 2 multiply with s plus 4. So we have equal k over s multiply with s plus 2 and s plus 4. The first question is draw the approximate root locus. So firstly, we need to find the of number of zeros. Number of zeros is equal to 0 because there is no s in the numerator, and n equal number of pole equal 3 because we have 3 s here. So s1 equals 0, s2 equal minus 2, and s3 equal minus 4. In the second step, we need to find the number of branch. Number of branch equal max n and m. So here it's equal 3. After that, we need to find the number of asymptote. It's equal n minus m. 3 minus 0. It's equal 3. After that, we need to find the intersection with asymptote with the real axis. It's equal over n minus m. So it's equal 0 minus 2 minus 4 minus 0 over 3. This equal minus 2. And the angle. The angle is equal 2k plus 1 over n minus m. So we need 3 alpha here. Alpha 1 is equal Here k firstly equals 0 equals 60 degree, alpha 2 directly minus 60, and alpha 3 is equal, here if k equal 1, 3 with 3 is equal 180. After that we need to find, here we have the first 0 at 0, the second at minus 2, and the third, or you can say the second in minus 2, and the third in minus 4. Here we have the ball. Here we have the first branch and the second branch to infinity. And we have 3 at 2, and here we have minus 60 degree. And the third angle is equal 180 degree. So after that we need to define this cross-section area between the asymptote and the imaginary axis. To find this intersection, we need to find 1 plus d multiplied with h equals 0. It's equal s multiplied with s plus 2 s plus 4 plus k equal to 0. So it will be s square s cubed plus 6s square plus 8s plus k equals 0. And we need to define the k equal minus s cubed plus 6s square plus 8. Here we have 8s and now dk over ds equal minus 3s square plus 12s plus 8 equal to 0. So we have two roots here. S1 equal minus 0.8 and S2 equal minus 3 minus 3.2. So minus 0.8 is located here. So it is valid, but 3.2 we ignore it. After that, we can select this or we can rewrite it s cubed plus 6s square plus 8s plus k equal to 0. And by use the root rules, s square, we find the range of k. And here we have 1, 6, 8, and k. So here we have 6 multiplied with 8, it is 48, minus k multiplied with 1 over 6. And here we have 0, so directly here we have k. So k it will be less than 48 and higher than 0. And if we need the, the intersection point here, so we need the critical point. If k equal 48, we select this row to find it. 6s square plus k equals 0 and k equal 48. 6s square plus 48 equals 0. So the first root is equal minus 2 square root of 2 j 2 square root of 2j, and the second one is equal minus 2 square root of 2 J. So here it's equal to square root of 2 J. And here we have minus 2 square root of 2 J. When K equal 48. And here also K equal 48. And here K equals 0. And in this point, here we have 0.8. This is the first branch. And here the second branch. So the final root locus draw it like that. The first branch, here we have 0.8. And here we have 2 square root of 2J. And the second one, here by positive, and here negative. And here we have the third one to infinity. Here when K equal 48, K equal 48. And here K equals 0. Minus 4, minus 2, and 0. The second question, comment of the time response under damped, critically damped, over damped, and stability of K. Okay, if we select K between 0 and 0.8, it is over damped. Because all root in the real axis, the negative real axis. If K equal 0.8 is critically damped because the roots are meet in the breakaway point. And here, if k bigger than 0.8 and less than 48, it is under damped because the root it's become the complex conjugate in the negative side. And if k equal 48, it's marginally damped. It's marginally stable, not marginally damped. Because the root it's in the imaginary axis. And if k bigger than 48, the system will be unstable. And here, compare the result. All needs step to draw the roots locus diagram by doing this same process in the MATLAB environment. So here are draw. If we use the MATLAB, S equal transfer function S, and here we have G multiply with H, it's equal 1 over S multiply with S plus 2 multiply with S plus 4. This is our transfer function. And here we have the pole and zeros map of this G multiply with H and the root locus of this function. So this is our root locus diagram. Here we have the first pole in 0, and here minus 2, and here 4, and here it is 0.8 or 0.9 minus 0.8. Yeah, and the intersection it will be positive 2.9 I. I think it's 2.2 multiplied with square root of 2. It's equal, and here the negative. Yeah, the negative 2 point something. So it's the same. In the second question, there are three operational amplifiers connected to the cascade in a control system. The waveforms are as shown on this side. Okay, according to this first question, draw the approximate connection and find the parameters value used. Okay, firstly, This is the input signal Vin equal DC 1 volt. In this figure, in the first stage, the output will be minus 0.5. So V out 1 equal minus 0.5. So the first voltage gain A1 equal V out over V in. So it's equal minus 0.5 over 1. It's equal 0.5. In the second one, the output from 0 to 4. So the output it will be like a ramp function. It's equal minus 2 over S V out V in. Because in the second one, we use integrator amplifier. So the V out equal minus 1 over RC multiply with integration from 0 to 4 V in dt. And here V in equal 0.5 minus 0.5. So here we have 0.5 multiply with RC. Multiply with 4. So the AV2 will be V out over V in 0.5 0.5 multiply with 4 over RC over 0.5 minus 0.5. So we can cancel this and you can say 4 or minus 4 over RC. And let's we say RC equal 2S. So AV2 equal minus 2 over S. And the third one, the V out equal minus 1. So AV 3 equal minus 1 over 1. So it will be minus 1. So the final diagram, firstly, the input like this in 1. The output from the first stage is equal, it will be shifted by 0.2, 0.5. And the second stage from 0 to 4. But here we're gonna start from 0.1, from 0.5 to 4.5. And the last stage, it will be shifted by 0 point, by 1, by minus 1. Shifted to low. We're gonna start here. Minus 0.5. And here it will be 3.5. So this is the final result. In the second question, if the op-amp used in the circuit are connected in parallel, okay, and pass through the collector with the gain of 1, obtain the transfer function with the circuit, okay. The transfer function of S total is equal A1 plus A2 plus A3. So it will be minus 0.5 minus 2 over S minus 1 minus 1.5 minus 2 over S. So it will be minus 1.5 S minus 2 over S. So this is the transfer function T of S. In the third question, implement the system in MATLAB. Okay, in MATLAB we have this code. Firstly, we defined S as a transfer function, and we have H total. H total is equal minus 1.5 multiply with s multiply with plus 2 over s, this function. And we have the time between 0 to 1 second to 10 second. V in one size is for bullet RC equals 0.5, and here we have V0 here we have V1 V out 1, and here we have V out 2, and here we have V out 3. So let's run the code. So the first one, V in inflow from 1 and DC, V out 1 from 0.5, yeah. V out 3 0 to 4, yeah, 0 to 4 at 4. V out 3 here minus 1, and the total V out, it's a green one, from minus 1.5 at 4 second to 3.5, like here. So it's a similar. In question number 3, the open loop transfer function of the unity feedback control system given and below. System type continuous state error. Firstly, specify the type of the system. Here we have s square plus 5. So this denominator, the type is equal 1, type 1. Because here the highest order is 2. The second question calculates the continuous state error for unity digit input. So we need to find ESS. Firstly, we need to find KB. KB equal limit when S goes to 0 of the U of S equal limit here we have 10 over S multiply with S plus 5. So K equal infinity. So ESS error equal 1 over 1 plus KB. So it's equal 1 over infinity. It's equal 0. So here there is no error. Second question. If the unit ramp input is applied for the same system to find. So the key of S will be 5 or 10 over S plus 5. So we need to find KV. KV equal limit when s goes to 0, 10 over s plus 5. So k equal 10 over 5 equal 2. So ESS will be 1 over 1 plus 2. No, here we have k over kv. So it's equal 1 over 2, it's equal 0.5. Comparison with the standard quadratic system, closed loop system. We need to find the closed loop system of this g of s. So the closed loop system will be g of s over 1 plus g of s. So it's equal 10 over s square plus 5 plus 10 s square plus 2s plus 5s plus 10. And here we have the standard form s square plus 2 the damping rate multiply with the natural frequency s plus the natural frequency square equal to 0. We need to find the natural frequency of the system and the damping rate. Here directly the natural frequency square equal 10. So omega n equal square root of 10 and 2 multiply with the damping rate multiply with omega n equal 5. So it's equal 5 over 2 multiply with square root of 10. It's equal 0.79. By using the MATLAB or Simulink, obtain the unit step response of the system using MATLAB or Simulink. Okay, we can go to the Simulink. This is our function. The numerator equal 10, the denominator equal s square plus 5s plus 10. Unit system transfer function numerator and numerator. Step info and step the system. So firstly, this is the rise time 0.7, transient time 1.1, setting time 1.16, setting minimum 0.9, and settling maximum 1.01, overshoot 1.7, undershoot equals 0, and the peak equal 1.01, and the peak time 1.6 seconds. And here our step response. Final question, we need to find the maximum overshoot, MP. MP equal exponential minus pi multiply with the damping rate over square root of 1 minus the damping rate square. It's equal multiply with 100%. Maximum overshooting equal 1.17%. Second question, the rise time TR. TR equal approximately 1.8 over the natural frequency. It's equal 1.8 over square root of 10. It's equal approximately 0.57. And finally, we need to find the settling time, TS. TS approximately equal 4 over 2 multiply with the damping rate multiply with the natural frequency. It's equal 4 multiply over 2 multiply with 0.79 multiply with square root of 10. It should be 1.6 second, and here we have second. So settling time 1.16. Yeah, here we have one. Also, the rise time here it's equal 0.7. I think we have a little bit different here. It is not similar, but it is. Yeah, we have a small different here in this result.